Hello there, and welcome to Life Beyond Seen, a quiet place where curiosity slows down, thoughts soften, and the world becomes just a little less loud for a while. Wherever you are right now, whether the day is ending or just beginning, I'm glad you're here. Tonight, we're going to drift toward a place on Earth that almost no one has ever seen with their own eyes. A place so deep and so resistant to visitors that even our best machines hesitate before going there. It's part of our planet that exists beyond sunlight, beyond weather, beyond anything that feels familiar, and yet it's been there all along, patiently waiting beneath the surface of the ocean. The topic tonight is not a mountain or a distant planet, but a trench. A long, narrow scar in the seafloor that stretches farther down than Mount Everest reaches up. A place that doesn't announce itself, doesn't shimmer on the horizon, and doesn't reward curiosity easily. The Mariana Trench has been called the deepest place on Earth, but that description almost feels too simple, too tidy, for something that resists exploration as strongly as it does. People often ask why we haven't explored it properly yet, why so much of it remains unseen, unmapped, and largely untouched. After all, we've landed probes on Mars, sent spacecraft beyond the edge of our solar system, and built machines that can see galaxies billions of light years away. So why does this immense feature, right here on our own planet, still feel out of reach? That question is where we'll begin, gently and without rushing. Because the answer isn't just about technology or danger or cost. It's about the way the trench exists, the conditions it creates, and the quiet ways it pushes back against intrusion. It's about pressure that doesn't forgive mistakes, darkness that absorbs everything, and distances that don't behave the way we expect them to. And it's also about human limits, not just physical ones, but psychological ones too. The trench isn't dramatic in the way volcanoes are dramatic. It doesn't explode or glow or roar. It simply waits, unchanged, indifferent to schedules and headlines. Before we drift any deeper into it, let me ask you something, just as a small pause to ground us here for a moment. Where are you listening from right now? Is it late where you are, or early? Are you winding down, or just looking for a quiet place to rest your thoughts for a while? It's interesting to think that while we're talking about a place where time seems almost irrelevant, you and I are each anchored to a specific moment, a specific hour, wherever we happen to be. The ocean doesn't care what time it is, but we still do, even when we're trying not to. If you find this kind of slow exploration calming, or if it helps you relax after a long day, you might consider liking the video or subscribing to the channel. It's a small thing, but it helps this quiet corner reach others who might be looking for the same kind of unhurried curiosity. There's no rush to do it now. The trench isn't going anywhere, and neither are we. When people imagine unexplored places, they often picture jungles, frozen poles, or distant planets. Places that are visibly hostile or obviously remote. The Mariana Trench doesn't look threatening from above. From the surface, the Pacific Ocean stretches out in familiar blues, broken by waves, clouds reflected on the water, ships passing by without any sign of what lies beneath them. There's nothing to suggest that beneath those moving patterns is a vertical drop so extreme that it changes the rules of physics for anything that enters it. In a way, that's part of the reason the trench refuses to be explored. It hides in plain sight. There's no clear boundary where the ocean suddenly announces that it's about to become something else entirely. You don't cross a line and feel the shift. You descend slowly, meter by meter, and with each step downward, the environment becomes less forgiving, less familiar, less interested in accommodating visitors. Exploration usually depends on feedback. We go somewhere, we observe, we adjust, we learn. The trench doesn't offer that kind of conversation. It doesn't adapt to us. It doesn't respond in helpful ways. The idea of going deeper has always carried a strange weight in the human imagination. We're comfortable moving across surfaces. We build roads, cities, borders. Depth is different. Depth removes landmarks. It removes orientation. It takes away the sky, the horizon, and eventually even the concept of direction as we normally understand it. In the open ocean, depth increases gradually, but the Mariana Trench drops away with an abruptness that feels almost intentional, as if the planet itself decided to carve out a place that would remain difficult to reach. Even measuring the trench was a challenge for a long time. Early attempts relied on weighted lines dropped from ships, a slow and imprecise process that could take hours just to confirm that the bottom was far deeper than expected. Each new measurement seemed to suggest that the trench was deeper than previously thought, as if it were quietly correcting our assumptions. Modern sonar has improved our understanding, but even now large sections remain only roughly mapped. The trench is narrow, uneven and complex, not a smooth canyon but a jagged, folded structure shaped by immense geological forces. And then there's the pressure. Pressure is one of those concepts that's easy to describe but difficult to fully grasp until you're confronted with its consequences. At sea level, the pressure on your body is something you never think about. It's simply there, balanced, unremarkable. As you descend into the ocean, pressure increases steadily, pressing in from all sides. By the time you reach the depths of the Mariana Trench, that pressure is so extreme that it can crush steel, shatter glass and collapse most structures instantly if they're not designed with extraordinary precision. This is one of the simplest reasons exploration is so rare. It's not enough to build something strong. It has to be strong in exactly the right way, without weak points, without flaws, without materials that behave unpredictably under stress. A single seal, a single joint, a single microscopic defect can mean total failure. And failure at those depths doesn't leave much behind to study. It's silent, immediate, and final. But even pressure isn't the whole story. Darkness plays its part too. Sunlight fades quickly in the ocean, and long before you reach the trench, light has already disappeared completely. What remains is a darkness so complete that it isn't like night. There are no stars, no moon, no distant glow. Light has to be carried with you, generated artificially, and even then it only reaches a short distance before being swallowed by the water. Exploration becomes a matter of illuminating small pockets of space in an otherwise endless void. This changes how observation works. Cameras struggle, depth perception becomes unreliable, movement feels slower, heavier, every action takes more time, more energy, more planning. Even sound behaves differently, travelling long distances in strange ways, echoing unpredictably. Communication with the surface is delayed, distorted, sometimes lost entirely. The deeper you go, the more isolated you become, not just physically but informationally. The trench cuts you off from the world above in ways that are difficult to simulate anywhere else. And yet, despite all of this, we have tried. Humans have always tried. There's something about an unanswered question that pulls at us, even when the answer doesn't promise comfort or reward. Over the decades, a handful of missions have reached the deepest known points of the trench, each one treated as a singular event rather than the beginning of sustained exploration. These descents are rare, expensive and risky, and they tend to reveal just how hostile the environment remains. What's striking is how little time these missions can actually spend at the bottom. Reaching the trench takes hours, preparing for the descent takes years, but once there, the window for observation is brief. Systems are under constant stress, power is limited, the margin for error is nearly non-existent. Exploration becomes a race against failure, not a leisurely process of discovery. This raises an uncomfortable question that often goes unspoken. Even if we can go there, should we? The trench is one of the least disturbed environments on Earth. Its isolation has protected it from many of the impacts humans have had elsewhere. Every expedition risks introducing contaminants, noise, disruption. The act of observation itself changes the environment, even when done carefully. In a place so stable and so slow to recover, those changes matter. As we move forward, we'll look more closely at these limits, not just the physical ones, but the practical and ethical ones as well. We'll talk about the machines we send down, the ones that return damaged or not at all. We'll talk about the strange forms of life that exist under pressures that would instantly kill us, and what their existence tells us about the boundaries of life itself. We'll talk about why mapping the trench is still incomplete, why satellites can't simply solve the problem from above, and why the deep ocean remains one of the last true frontiers on our planet. For now, it's enough to sit with the idea that there is a place on Earth that quietly resists exploration, not through drama or danger in the traditional sense, but through persistence, through conditions that don't fluctuate, don't adapt, and don't compromise. The Mariana Trench doesn't need to scare us away. It simply exists on its own terms, and those terms are difficult for us to meet. And as we begin to drift from the surface toward deeper water, it becomes clear that this story isn't about conquering or solving the trench. It's about understanding why, even with all our tools and ambition, some places remain stubbornly beyond our reach, not because we haven't tried hard enough, but because the world is under no obligation to make itself accessible. From here, the surface fades, and the idea of depth becomes more than just a number. When people talk about maps, they usually imagine certainty. Lines drawn with confidence, labels placed neatly, borders agreed upon, distances measured and fixed. A map is supposed to be a declaration that someone has been here, measured this, understood it well enough to flatten it onto paper or a screen. Even when maps are wrong, they tend to be wrong in familiar ways. A river bends slightly differently than expected. A mountain is taller than first thought. A coastline turns out to be more jagged up close, but the ocean, especially the deepest parts of it, has a habit of resisting that kind of certainty. And nowhere does it resist more quietly, or more completely, than the Mariana Trench. From a distance, the trench is easy to miss. On a global map, it appears as a thin, curved line in the Western Pacific, east of the Philippines, south of Japan. It doesn't dominate the page. It doesn't demand attention. If you didn't know what you were looking at, you might assume it was just another feature, another wrinkle in the vast blue space that covers most of the planet. But that thin line represents a vertical drop so extreme that it breaks our usual ways of thinking about geography. It's not just deep, it's disproportionately deep. Deep enough that the word itself starts to lose its meaning. The trouble with mapping the trench begins with a simple problem. Water gets in the way. Light doesn't travel far underwater, which immediately removes one of our most reliable tools for observation. On land, mapping is often a visual process. You can see landmarks, horizons, gradients. Even in dense forests or harsh terrain, there is usually some visual reference to work from. Under several kilometers of water, there is none of that. Darkness is absolute, and pressure makes traditional instruments fragile. The seafloor becomes something you have to infer rather than observe directly. Early attempts to understand the trench relied on remarkably simple methods. Ships would stop above suspected deep points and lower weighted lines into the water, waiting to see how long it took to reach the bottom. These measurements were slow, imprecise, and often misleading. Currents could drag the line sideways. The line could stretch. The weight could land on a slope rather than the deepest point. Each reading was an estimate layered on top of assumptions. Still, these crude measurements hinted at something unusual. The numbers kept growing. Each expedition seemed to find a deeper point than the last, as if the ocean floor were quietly retreating every time someone tried to pin it down. As technology improved, sonar became the primary tool for mapping the ocean floor. The idea is straightforward. A ship sends out a pulse of sound, which travels through the water, hits the seafloor, and bounces back. By measuring the time it takes for the echo to return, scientists can estimate the depth below. This method works well in shallow and moderately deep waters, and it has given us detailed maps of much of the ocean floor. But the trench complicates things. Its walls are steep, its shape is irregular. Sound waves don't always behave predictably when they encounter such extreme terrain. Instead of clean echoes, sonar pulses can scatter, reflect multiple times, or return distorted. The trench's narrow profile means that a single sonar pass might miss the deepest point entirely. To get a clearer picture, ships would need to pass back and forth repeatedly, at different angles, with overlapping coverage. Even then, the data would be incomplete. Each pass is just a thin slice, and stitching those slices together into a coherent map introduces errors and uncertainties. The deeper the water, the more those uncertainties accumulate. This is why maps of the Mariana Trench often look less confident than maps of land. Contour lines are broader, gradients are smoother, sharp features are implied rather than defined. In some areas, large sections are labelled with estimated depths rather than precise measurements. These are the places where maps quietly admit their limits. They don't say, "Here be monsters," the way old maps once did, but the message is similar. This area has not been fully seen. There's also the matter of scale. The trench is long, stretching for more than 2,500 kilometres, but it's also narrow compared to that length. Its deepest point, often called Challenger Deep, is not a single hole, but a complex region with multiple depressions. Mapping something like that requires a level of resolution that is difficult to achieve at such depths. It's like trying to map the shape of a winding canyon while hovering several kilometres above it, using only sound and time delays. Satellites, which have revolutionised mapping on land, don't solve this problem either. They can't see through water. What they can do is measure tiny variations in the height of the ocean surface caused by gravity. Massive underwater features like seamounts and trenches slightly alter Earth's gravitational field, which in turn affects the shape of the sea surface above them. By measuring these subtle changes, scientists can infer the general shape of the seafloor. This method has helped identify large features and refine existing maps, but it lacks detail. It can tell you that something deep is there, not exactly what it looks like. As a result, the trench exists in a strange cartographic state. It is known, named, and broadly understood, yet still largely unmapped in detail. We know where it is. We know how deep it gets. But much of its structure remains abstract, represented by smooth gradients and average data rather than direct observation. In a world where high-resolution images of distant planets are readily available, this feels almost backwards. How can something so close, so undeniably part of our own planet, remain so visually elusive? Part of the answer lies in how hostile the environment is to sustained exploration. Mapping is not a single event. It's a process that improves with repeated visits, adjustments, and corrections. On land, this happens constantly. Roads are built, satellites pass overhead, people travel and report back. The trench doesn't allow for that kind of iterative refinement. Each visit is expensive, risky, and limited in duration. Instruments deployed there have to survive pressures that would destroy most equipment. When they fail, recovery is often impossible. Lost instruments become part of the trench, not sources of data. There's also a psychological element to mapping that often goes unnoticed. Maps are made by people, and people are drawn to places that promise utility or familiarity. Coasts are mapped in detail because they're used for navigation and trade. Rivers are mapped because they support agriculture and settlement. Even remote mountains attract attention because they can be climbed, photographed, named. The trench offers none of these incentives. It can't be traversed. It can't be settled. It doesn't provide resources that are easily extracted. Its value is scientific, abstract, and long-term. That makes it harder to justify the sustained effort required to fully map it. When maps give up, they don't do so dramatically. There's no announcement. The process simply slows. Data points become sparser. Confidence intervals widen. Labels become vaguer. In the case of the Mariana Trench, this means that much of what we know is based on inference rather than direct measurement. We know the general shape because tectonic forces behave in predictable ways. We know the approximate depth because repeated measurements converge on similar numbers. But the fine details, the textures and contours that would make the trench feel real rather than theoretical, remain mostly hidden. This has consequences beyond cartography. Maps shape how we think about places. A well-mapped region feels accessible, even if it's remote. An unmapped one feels distant, even if it's close. The trench, despite being part of Earth's geography, often feels more alien than the surface of Mars. At least Mars has been photographed extensively. At least its craters and valleys are visible, named, and catalogued. The trench exists mostly as a concept, a set of numbers, a dark space on a map where precision fades. This sense of uncertainty feeds into the broader mystery of why the trench refuses to be explored. Exploration depends on a feedback loop between curiosity and comprehension. We go somewhere, learn something, refine our tools, and go back better prepared. When the initial learning is limited, the loop stalls. Each attempt to map the trench reveals how much remains unknown, reinforcing the idea that it is a place that does not easily yield to understanding. There's also the matter of change, or rather, the lack of it. On land, maps quickly become outdated because landscapes are dynamic. Rivers shift, cities expand, forests shrink. The trench changes on geological timescales, not human ones. Once a rough map exists, there's less urgency to update it, because nothing obvious is happening. This creates a paradox. The trench is stable enough to ignore, but unknown enough to remain mysterious. Even the language used to describe it reflects this tension. Words like deepest and darkest emphasize extremes, but they don't convey structure. They don't tell you what it's like down there, only that it's far removed from the surface world. Maps at their best turn extremes into familiarity. They take the unknown and make it navigable. The trench resists that transformation. It stays abstract, defined by absence as much as presence. And yet, this very resistance is part of its significance. The fact that maps struggle here is a reminder that Earth is not fully catalogued, not fully known. Despite centuries of exploration and decades of advanced technology, there are still places where our representations fall short. The Mariana Trench is one of those places, not because it is actively hiding, but because it exists under conditions that push our tools to their limits. As we move forward, it helps to keep this in mind. The trench is not refusing exploration out of malice or mystery in the dramatic sense. It is simply being itself. Its depth, pressure, darkness, and scale combine to create an environment where mapping becomes an exercise in approximation rather than certainty. Understanding why maps give up here is the first step toward understanding why exploration itself becomes such a slow, cautious process. From this point, the conversation naturally shifts from representation to experience. Once maps begin to blur, the next question is what it actually means to descend into such a place, to move beyond the limits of visualization and into conditions that fundamentally alter how matter behaves. Depth stops being a number on a chart and becomes something physical, something that shapes every decision and every design choice. And it's there, in that transition from mapped surface to unmapped depth, that the real resistance of the trench begins to show itself. There is a moment in the descent where light simply stops behaving the way we expect it to. It doesn't fade politely or linger as a dim glow. It thins out, weakens, and then disappears altogether, leaving behind a kind of darkness that isn't dramatic but absolute. This is what extreme depth really means, not just a large number measured downward, but the complete removal of something we rely on so completely that we rarely notice it at all. Sunlight is so constant in human life that its absence feels unnatural, even unsettling, and yet in the depth below the surface that absence is the norm. In the open ocean, sunlight can penetrate surprisingly far at first. The upper layer, known as the sunlit zone, extends down a couple of 100 meters. Here, light still fuels photosynthesis. Tiny plants drift and grow, forming the base of the marine food web. Fish move easily through clear water. Colours still exist, though they slowly begin to shift. Reds disappear first, then oranges and yellows, leaving behind blues and greens that travel farther. Even at this stage, depth is already changing perception, quietly editing reality by removing parts of the visible spectrum. Below that lies a transition, a dim region where light weakens enough that photosynthesis can no longer occur. This is where the sun's influence ends in any practical sense. What little light remains is not enough to support plant life. It becomes a place of silhouettes and shadows where shapes are visible but details are lost. By the time you descend farther still, light is no longer a factor at all. Not a faint glow, not a distant shimmer. Nothing. Darkness becomes complete and permanent. The deepest parts of the ocean, including the Mariana Trench, exist entirely beyond the reach of the sun. No sunrise has ever touched them. No seasonal change alters their illumination. Day and night have no meaning there. Time does not arrive marked by light. It arrives only through motion, pressure, and slow geological change. This is a difficult idea to internalize because our sense of time is so closely tied to light. We wake with brightness and sleep with darkness. Remove that cycle, and the environment becomes fundamentally alien. Extreme depth is often described using vertical distance, but that description misses something essential. Depth is not just how far down you go, it is how much the environment changes as you descend. Each layer strips away assumptions. Gravity still pulls, but buoyancy begins to dominate. Sound travels farther than sight. Temperature drops and stabilizes. Movement slows. Objects behave differently. Even materials we trust on the surface start to fail in unexpected ways. The absence of sunlight reshapes life in profound ways. Without photosynthesis, there is no easy source of energy. Nothing grows in the traditional sense. There are no plants, no algae, no drifting blooms of life fueled by light. Instead, energy arrives from above, falling slowly like debris. Dead organisms, waste and organic fragments sink from the surface, forming what scientists call marine snow. It drifts downward in tiny pieces, taking days or weeks to reach the depths. By the time it arrives, it is sparse, scattered, and unpredictable. Life that exists in these depths has adapted to this scarcity. Creatures move slowly to conserve energy. Many have transparent bodies or muted colours because camouflage works differently when there is nothing to see. Some generate their own light through bioluminescence, not to illuminate the environment, but to communicate, attract prey, or confuse predators. Light here is no longer something received from the outside. It is something produced deliberately, used sparingly, and often briefly. From a human perspective, the lack of sunlight creates immediate practical problems. Cameras require light. Human eyes require light. Even instruments that don't rely on vision are often designed and tested in environments where light is present. In the deep ocean, every bit of illumination has to be brought along, generated on board, and powered continuously. This limits how long exploration vehicles can operate. Lights consume energy, generate heat, and attract attention from organisms that may interfere with equipment. Darkness also changes scale. Without visual reference points, distances become hard to judge. A rock might be the size of a fist or the size of a car. A slope might be gentle or dangerously steep. In the trench, walls drop sharply, and the seafloor is uneven. Without light, navigation becomes a careful process of interpreting sonar readings and sensor data rather than relying on direct observation. Exploration slows not because nothing is happening, but because everything has to be verified through indirect means. Temperature adds another layer to what extreme depth really means. At the surface, ocean temperatures fluctuate with weather, seasons, and latitude. In the trench, temperature is cold and stable, just a few degrees above freezing, it does not change significantly over time. This stability sounds comforting, but it creates challenges. Cold affects batteries, electronics, and materials. Lubricants behave differently. Metals contract. Plastics become brittle. Systems that work perfectly at the surface may fail quietly and suddenly in the cold darkness below. Pressure, which increases relentlessly with depth, interacts with this cold and darkness in complex ways. At the bottom of the trench, pressure is more than 1,000 times greater than at sea level. This pressure is not directional. It presses in from all sides equally, crushing air-filled spaces instantly. Any exploration vehicle must either be completely solid or perfectly sealed. Even then, microscopic imperfections can become points of failure. A seal that holds at moderate depth may leak or collapse entirely under extreme pressure. This combination of darkness, cold, and pressure creates an environment where mistakes are unforgiving. On land, a failed expedition might mean turning back. In the trench, failure often means total loss. There is no rescue. There is no quick fix. Communication with the surface is delayed and limited. Once a vehicle descends beyond a certain point, it is largely on its own. This reality shapes how missions are planned. Everything must be tested repeatedly. Redundancy is built into every system. Even then, success is never guaranteed. Extreme depth also changes how sound behaves, which becomes crucial when light is absent. Sound travels farther in water than in air, and in the deep ocean, it can propagate over long distances with little loss. This allows for communication and navigation using acoustic signals. But sound is not precise in the way vision is. Echoes overlap, signals distort. Noise from distant sources can interfere unexpectedly. Interpreting acoustic data requires expertise and patience. It is a language learned slowly, often through trial and error. The psychological impact of extreme depth should not be underestimated either. For the rare human descents into the trench, the experience is not one of adventure in the traditional sense. There is no sweeping view, no sense of movement through space. The descent takes hours. Outside the vessel there is only darkness. Inside there is the constant awareness of pressure. Every sound becomes noticeable. Every vibration invites attention. The environment offers no reassurance. It does not respond. It does not acknowledge presence. Even remotely operated vehicles and autonomous probes are affected in subtler ways. Without sunlight, energy must be carried or generated. Solar power is useless. Long missions require careful energy budgeting. Every sensor, every motor, every light must justify its use. Data storage becomes precious. Transmission bandwidth is limited. Exploration becomes an exercise in prioritization. What do you observe when you cannot observe everything? What do you record when you cannot stay long? Extreme depth also complicates the idea of return. Ascending from the trench is not simply reversing the descent. Materials decompress, temperatures change, systems must survive both extremes. Pressure vessels that perform well at depth must also tolerate the stresses of ascent. Life brought up from the trench often does not survive the journey. Organisms adapted to immense pressure cannot function at the surface. Their bodies are built for a world that does not exist above. This makes studying deep-sea life particularly challenging. Observation must often happen in place, through cameras and sensors rather than through direct sampling. Even then, the presence of exploration equipment alters the environment. Lights attract organisms that would not otherwise be there. Noise may disrupt natural behaviour. The act of observation becomes part of the system being observed, complicating interpretation. When people ask why the deepest parts of the ocean remain unexplored, the answer often focuses on danger. But danger is only part of it. Extreme depth represents a fundamental shift in conditions, not just an increase in difficulty. It is not a matter of scaling up surface technology. It is a matter of operating in a place where the basic assumptions of human experience no longer apply. No light, no warmth, no margin for error. This is why comparisons between deep-sea exploration and space exploration are common but imperfect. Space is hostile in obvious ways, but it is also empty. There is no pressure. Temperature extremes can be managed with insulation. Solar energy is abundant. Communication, while delayed, is relatively straightforward. The trench, by contrast, is dense, crushing and isolating. It presses back against every attempt to enter it. It absorbs light, dampens motion, and enforces patience. Understanding what extreme depth really means requires letting go of surface-based intuition. Depth is not just distance, it is transformation. Each kilometre downward removes another layer of familiarity. By the time sunlight is gone for good, the environment has already become something else entirely, a place where energy is scarce, time feels stretched, and the rules are written by pressure and darkness rather than weather and light. As we continue, the focus naturally shifts from the absence of sunlight to the force that replaces it as the dominant influence. Pressure does not just accompany depth, it defines it. It shapes every material, every movement, every decision. If darkness removes our ability to see, pressure removes our ability to be careless. And it is that relentless, invisible force that turns extreme depth from an abstract concept into a practical barrier, one that few machines and even fewer humans have ever crossed. When people imagine going deep underwater, they often picture the darkness first. They imagine cold, silence, maybe strange creatures drifting past. Pressure, if it comes to mind at all, is usually treated as an abstract force, something technical that engineers handle behind the scenes. But pressure is not a background condition. In the deep ocean, pressure is the environment. It is the defining feature that makes descent difficult, dangerous, and fundamentally different from almost any other form of exploration humans attempt. At the surface of the ocean, pressure feels normal because it is normal. One atmosphere of pressure presses down on everything equally, and our bodies are perfectly adapted to it. We don't notice it because it doesn't change, but water is heavy, much heavier than air. Every 10 meters you descend adds roughly another atmosphere of pressure. That means that at 100 meters, pressure is already 10 times what it is at the surface. At 1,000 meters, it is 100 times greater. The numbers climb steadily, without drama, without pause. By the time you reach the deepest parts of the ocean, including the Mariana Trench, the pressure is almost impossible to visualize. More than 1,000 atmospheres press in from all sides. That is the equivalent of having several dozen jumbo jets stacked on every square meter of surface area. Steel beams buckle under far less stress. Concrete fractures. Most familiar materials simply fail. What makes pressure especially unforgiving is that it does not attack from one direction. It does not push down like gravity or strike like a wave. It surrounds, it infiltrates, it finds weaknesses that would never matter on land. A hairline crack, a poorly seated seal, a microscopic bubble trapped during manufacturing can become catastrophic failure points. Pressure does not announce itself. It does not creak or groan in advance. It applies itself constantly, evenly, patiently. This is why going down is harder than it sounds, even compared to going into space. In space, pressure is absent. The challenge is keeping something in. Underwater, the challenge is keeping everything out. Any empty space becomes a liability. Air-filled compartments want to collapse. Flexible materials compress. Even solid materials behave differently under sustained pressure. Metals can fatigue. Polymers deform. Electronics short as water finds paths it should not be able to access. Designing vehicles for extreme depth is therefore less about strength in the traditional sense, and more about geometry and consistency. Rounded shapes are favoured because they distribute pressure evenly. Sharp corners concentrate stress. Flat surfaces bow inward. Windows, if they exist at all, must be small, thick, and perfectly shaped. The famous spherical pressure hulls used in deep-diving submersibles are not aesthetic choices, they are survival necessities. Even with ideal design, materials are pushed to their limits. Titanium alloys, specialized steels, and advanced composites are used because they maintain strength under compression and resist corrosion. But these materials are expensive, difficult to work with, and unforgiving during fabrication. Welding must be flawless. Machining tolerances are extremely tight. Every joint must be tested repeatedly, often to destruction, before it is trusted. Pressure testing itself becomes an ordeal. To simulate deep-sea conditions, engineers use hyperbaric chambers that can reproduce extreme pressures in controlled environments. These tests are slow and cautious because failure can be violent. When a structure collapses under pressure, it does so instantly. The energy released is immense. Implosions are not dramatic explosions outward. They are sudden, inward collapses that pulverize whatever is inside. This risk shapes how exploration missions are planned. There is no room for improvisation at depth. Everything must be known in advance. Redundancy is built into every system, not because redundancy makes failure impossible, but because it delays it. Backup systems buy time, and time is the most valuable resource during a deep descent. Pressure also complicates movement. Propellers, joints, and control surfaces must function reliably while being squeezed by enormous forces. Lubricants behave differently. Motors draw more power. Seals that work at shallow depths may leak or seize at greater ones. Even simple actions like adjusting a camera or changing orientation require careful calibration to avoid stressing components. Communication systems face similar challenges. Cables must withstand tension and pressure without snapping. Acoustic transmitters must operate reliably despite compression. Any breach allows water to enter at tremendous force, flooding compartments in fractions of a second. Once that happens, recovery is unlikely. For human occupants, pressure is even more unforgiving. Humans cannot survive exposure to deep-sea pressure directly. Our bodies are mostly water, but we rely on air-filled spaces to function. Lungs, sinuses, and ears collapse under pressure unless protected. This is why human descent requires rigid vessels that maintain internal pressure close to surface levels. Even then, the margin for error is non-existent. Psychologically, the knowledge of pressure is always present during manned dives. There is no visible reminder, no shaking or warning. The hull does not flex visibly. The pressure is felt only intellectually, as a constant awareness that the environment outside is exerting forces far beyond what the structure was ever meant to tolerate. Every sound inside the vessel is interpreted cautiously. A creak, a ping, a vibration can trigger immediate concern. Pressure also dictates how long missions can last. Materials under constant stress degrade over time. Even if a vessel survives descent, prolonged exposure increases risk. Most deep dives therefore limit time spent at maximum depth. The goal is observation, not endurance. Gather data, record images, and begin ascent before fatigue becomes a factor. This creates another limitation. Exploration becomes brief by necessity. There is no lingering, no extended survey. The deepest places on Earth are visited like fragile exhibits, glimpsed quickly and left behind. This is not because scientists lack curiosity, but because pressure enforces caution. It also explains why many missions rely on uncrewed vehicles. Removing humans reduces risk, but it does not remove the pressure problem. Robots and probes still face the same forces. They still fail. In fact, many have been lost. Pressure does not discriminate between organic and mechanical life. It applies itself equally. Pressure shapes everything about the deep ocean environment. It influences which organisms can survive, how they function, and how they reproduce. It affects chemical reactions, structural biology, and energy use. Life in the trench is built for compression. Proteins fold differently. Cell membranes are structured to resist collapse. These adaptations are so specific that bringing deep-sea organisms to the surface often kills them, not because of temperature or oxygen, but because of decompression. Understanding pressure is therefore key to understanding why exploration progresses so slowly. It is not a matter of bravery or ambition. It is a matter of physics. Pressure increases predictably, relentlessly, and without compromise. It cannot be negotiated with. It cannot be bypassed. As depth increases, pressure becomes the primary constraint, overtaking darkness, temperature, and distance. It dictates what can be built, how long it can last, and how often it can be used. It turns the ocean into a layered barrier where each additional kilometre adds not just distance, but exponentially greater risk. And as pressure tightens its grip, the environment becomes quieter, slower, and more resistant to intrusion. The deeper you go, the less forgiving the world becomes, until exploration itself turns into a careful balance between curiosity and survival. From here, the conversation naturally moves from the force that crushes to the environment that remains unchanged beneath it, a place defined not by motion or weather, but by stillness that has endured for millions of years. Far below the reach of storms, tides, and seasons, there is an environment that does not hurry. It does not react quickly, and it does not change its mind. Once you pass beyond the layers shaped by sunlight and surface weather, the ocean settles into a state that feels almost permanent. This is the world of the deepest trenches, including the Mariana Trench, where cold, darkness, and stillness are not temporary conditions but defining features. Temperature is one of the first things that stabilizes as depth increases. Near the surface, ocean temperatures rise and fall with the sun, the wind, and the movement of currents. Warm water drifts, cold water sinks, and layers mix and separate constantly. But as you descend, those variations smooth out. By the time you reach the depths of the trench, the temperature hovers just above freezing and remains there year after year, century after century. It does not matter whether there is a heat wave on the surface or an ice age on land. The trench stays cold. This cold is not sharp or biting in the way we imagine cold on land. It is steady and pervasive. It does not rush in or recede. It simply exists, filling every space, pressing against every surface. For machinery, this means that materials are always operating at the lower edge of their temperature tolerance. Metals contract slightly and remain contracted. Plastics lose flexibility. Batteries drain faster. Chemical reactions slow. Nothing warms up unless energy is actively supplied, and even then that warmth is quickly absorbed by the surrounding water. Darkness, too, is not an event but a condition. Once sunlight disappears, it never returns. There is no dawn, no dusk, no gradual shift from day to night. Darkness does not fall, it is already there. This has a subtle but profound effect on how the environment behaves. Without light, there is no daily rhythm driven by sunrise and sunset. There are no shadows moving across the seafloor. There is no visual signal that time is passing. In most places on Earth, change is obvious. Leaves grow and fall, snow melts. Rivers rise and shrink. Even in deserts, wind reshapes dunes and erosion slowly carves rock. In the trench, change happens so slowly that it is almost imperceptible. Sediment drifts down from above at a pace measured in millimeters over centuries. Geological movement occurs over millions of years. From a human perspective, the environment is effectively frozen in time. This patience is not passive. It is enforced by the conditions themselves. Cold slows chemical reactions. Darkness removes energy input. Pressure limits movement. Together, these factors create a system where rapid change is not just unlikely, but physically discouraged. Anything that happens here happens slowly. Decay is slow. Growth is slow. Movement is slow. For living organisms, this means life proceeds at a different pace. Metabolisms are reduced. energy is conserved carefully. Many deep-sea creatures live long lives by surface standards, growing slowly and reproducing infrequently. There is no advantage to speed when food is scarce and conditions are stable. Survival favours efficiency and patience rather than aggression or rapid expansion. From an exploration standpoint, this unchanging environment presents a paradox. On one hand, stability makes prediction easier. Once you know the temperature, pressure, and chemistry of a region, you can assume they'll be the same next year and the year after that. On the other hand, stability removes urgency. There is no seasonal window to exploit, no brief moment when conditions improve. The trench will be just as cold and dark tomorrow as it is today. If you do not go now, you can go later, and that later has a way of stretching indefinitely. The absence of weather is particularly striking. Storms churn the surface ocean, mixing layers and redistributing nutrients. Waves break, winds shift, and energy is transferred constantly. None of that reaches the trench. By the time surface disturbances travel downward, they have dissipated into gentle currents or vanished entirely. The deepest parts of the ocean are shielded from surface chaos by sheer distance and density. What happens above is largely irrelevant below. This isolation reinforces the trench's resistance to exploration. Many scientific missions rely on timing. Satellites pass overhead, ships coordinate with weather windows, aircraft wait for clear conditions. In the trench, timing loses much of its meaning. You're not racing against storms or daylight. You're racing against equipment limits, budgets, and human attention. The environment itself is content to wait. Cold, darkness, and pressure also shape the chemistry of the trench. Oxygen levels are low but stable. Nutrient input is minimal. Chemical reactions that would proceed quickly near the surface crawl along here. This has implications for corrosion, material degradation, and biological processes. Metals corrode differently. Organic matter breaks down slowly. Traces of human activity, once introduced, may persist far longer than expected. This is one reason why some scientists approach trench exploration with caution. In an environment where change is slow, recovery from disturbance is also slow. A footprint left on the seafloor may remain visible for decades. Noise introduced by equipment may alter behaviour patterns that take generations to return to baseline. The trench is not fragile in the sense that it will collapse, but it is sensitive in its own way, not designed to absorb rapid disruption. The patience of the trench can be unsettling. Humans are accustomed to environments that respond. Turn on a light and the room brightens. Start a fire and warmth spreads. In the deep ocean, actions have limited reach. Light illuminates only a small area. Heat dissipates quickly. Sound travels, but its effects are unpredictable. The environment does not acknowledge presence in any obvious way. It remains cold and dark regardless of activity. This lack of feedback affects how exploration feels. There is no sense of progress marked by changing scenery or conditions. A descent of several kilometers may look much the same through a camera feed. Darkness, sediment, occasional shapes drifting past. Without clear visual cues, it is easy to underestimate distance and effort. Going deeper does not feel like approaching a destination. It feels like continuing in the same state, only with increasing risk. Even the seafloor itself reflects this stillness. It is not a barren plain, but it is subdued. Features are softened by sediment. Sharp edges are rare. Everything looks worn down, not by erosion in the usual sense, but by time itself. Objects settle and remain. There is no wind to move them, no rain to wash them away. Gravity and pressure hold everything in place. For instruments deployed in the trench, this environment can be both a blessing and a challenge. On one hand, stable conditions mean that measurements are consistent. Sensors do not have to account for rapid fluctuations. On the other hand, long-term deployment requires systems that can operate reliably without maintenance in cold, dark conditions for extended periods. Any failure may go unnoticed for months or years. Any retrieval mission is costly and uncertain. This reinforces a pattern seen throughout trench exploration. Missions tend to be brief, targeted and conservative. There is little incentive to experiment aggressively when the environment offers no forgiveness. Each descent is planned carefully, with clear objectives and limited scope. The trench's patience encourages human caution. There is also a psychological dimension to this stillness. Humans are wired to respond to change. We notice movement, contrast, novelty. In an environment where nothing changes quickly, attention drifts. Time stretches. For those observing remotely, hours of footage may show little variation. This makes data analysis slow and demanding. Discoveries, when they happen, emerge quietly rather than dramatically. The cold, dark and patient nature of the trench also challenges storytelling. There are no sudden events, no clear milestones. Exploration does not unfold as a sequence of triumphs and setbacks, but as a gradual accumulation of small observations. This does not fit neatly into narratives of conquest or progress. The trench does not reward boldness. It rewards persistence, and persistence is expensive. Maintaining interest in a place that looks the same every time you visit requires sustained commitment. Funding agencies, institutions, and governments often prioritize projects with visible outcomes and short timelines. The trench, by contrast, offers long-term insight at the cost of immediate results. Its patience does not align well with human schedules, yet this unchanging environment is precisely what makes the trench scientifically valuable. It is a natural laboratory for studying processes that operate over long timescales. It preserves records of past events in its sediments. It hosts life forms adapted to conditions that are stable in ways few other environments are. Understanding it requires accepting its pace rather than trying to impose our own. As exploration continues, the trench remains indifferent. It does not become more welcoming with familiarity. It does not reveal itself more readily after repeated visits. Each mission encounters the same cold, the same darkness, the same quiet resistance. The environment does not care whether it is being studied or ignored. This indifference is not hostility. It is simply consistency. The trench is what it is, and it has been that way for a very long time. For explorers, this means that success is not measured by how much the environment changes, but by how well we adapt to it. As we move forward, attention naturally shifts from the environment itself to the question of who, if anyone, can function within it. The cold, dark patience of the trench sets the stage for understanding why human presence is so rare, and why machines, rather than people, have become our primary ambassadors to the deepest parts of the ocean. At some point, every discussion about the deepest parts of the ocean arrives at the same question, quietly but inevitably. If we can build machines strong enough to go there, why not send people? After all, humans have walked on the moon, lived aboard space stations for months at a time, and descended into caves so deep they seem to swallow sound itself. There is a powerful assumption that if a place exists, and if it can be reached, then surely a human presence is the ultimate goal. But the deep ocean, and especially the depths associated with the Mariana Trench, challenges that assumption in ways that are not immediately obvious. The problem with sending humans is not a single obstacle. It is a collection of limits that stack on top of one another until the margin for survival becomes vanishingly small. Darkness, pressure, cold and isolation all play their part, but none of them alone explains why people don't belong there for long. The deeper issue is that human bodies are not just poorly suited to the environment, they are fundamentally incompatible with it over extended periods. Human physiology is built around very specific conditions. We require a narrow range of pressure, temperature and chemical balance to function. Even small deviations can cause discomfort or injury. Larger ones can be fatal. On land and at the surface of the ocean, these conditions are naturally present. At depth, they are not. Every single requirement has to be artificially recreated inside a vessel, and every one of those systems has to function perfectly for the entire duration of a mission. Pressure is the most obvious constraint. Human bodies cannot withstand the pressure found in the deep ocean without protection. Even trained divers using specialized equipment are limited to depth that are tiny fractions of trench depth. Beyond a certain point, the risks of decompression sickness, nitrogen narcosis, oxygen toxicity, and physical collapse make direct exposure impossible. This means that any human presence in the trench must be inside a rigid, sealed vessel that maintains near-surface pressure. That vessel becomes the human environment. The ocean outside is no longer just a place. It is a constant threat. The hull is not a boundary so much as a fragile agreement between physics and engineering. Inside, the air must be breathable, the temperature controlled, and the humidity regulated. Carbon dioxide must be removed continuously. Oxygen must be replenished. Power must be stable. There is no redundancy beyond what is built in. If something fails, there is nowhere to go. This creates a psychological burden that is difficult to overstate. Humans are adaptable, but we are also acutely aware of risk when it cannot be escaped. In a spacecraft, there is the vastness of space outside, but also the knowledge that orbital mechanics and rescue missions exist, at least in principle. In the trench, rescue is not a realistic option. If a vessel becomes disabled at depth, recovery may be impossible. The descent itself takes hours. Ascent takes just as long, often longer. There is no rapid intervention. Isolation compounds this stress. Communication with the surface is limited and delayed. Radio waves do not travel well through water, so communication relies on acoustic signals, which are slow and bandwidth limited. Conversations are not fluid. Information arrives in fragments. In an emergency, this delay matters. Decisions may have to be made without immediate guidance. The crew must be self-reliant in a way that few environments demand. Time perception also changes. A deep-sea descent is not dynamic. There is no changing scenery, no visible progress toward a destination. Darkness outside the viewport remains constant. The pressure gauge climbs steadily, but that number is abstract. Hours can pass with little sensory input. For some, this monotony is calming. For others, it is unsettling. Human minds are not designed to operate indefinitely in environments with minimal stimulation and high stakes. Physical discomfort adds another layer. Space inside deep-diving submersibles is extremely limited. To minimize hull size and maximize structural integrity, interiors are cramped. Crew members may be seated for the entire duration of the dive, unable to stand or move freely. There is no privacy. Basic needs must be managed carefully. Even simple actions require planning. Fatigue accumulates, but rest is difficult. Then there is the issue of duration. Human missions to extreme depths are necessarily short, not because curiosity is satisfied quickly, but because endurance is limited. The longer a human remains inside a pressure vessel, the more likely it is that something will go wrong, either mechanically or biologically. Even if all systems function perfectly, the strain on the human body and mind increases with time. This is where comparison with robotic exploration becomes unavoidable. Machines do not require air. They do not experience fear or fatigue. They can operate in darkness without discomfort. They can be designed to tolerate pressure without concern for psychological effects. When a robotic probe fails, the loss is financial and scientific, not human. This does not make such losses trivial, but it changes the calculus of risk. As a result, most modern trench exploration favours uncrewed systems. Remotely operated vehicles and autonomous probes can descend where humans rarely go. They can stay longer, take greater risks, and be sacrificed if necessary. From a purely practical standpoint, this makes sense, but it also means that direct human experience of the trench is limited to a handful of brief descents, each one treated as a rare and carefully controlled event. There is also the matter of perception and interpretation. Humans are excellent observers in familiar environments. we notice patterns, anomalies, and subtle cues. In the trench, many of those cues are absent or misleading. Visual information is limited. Sensory input is filtered through cameras and instruments. The human presence adds value in decision-making and adaptability, but it does not necessarily improve raw observation at depth. In some cases, it complicates it by introducing human bias and stress responses. The body itself becomes a constraint. Humans require a certain level of comfort to function optimally. Cold affects concentration. Cramped spaces affect circulation. Dehydration, hunger, and fatigue degrade performance. These are manageable issues in many extreme environments, but in the trench, they interact with isolation and risk in ways that amplify their effects. There is also a subtle but important ethical dimension. Sending humans into an environment where rescue is unlikely raises questions about acceptable risk. Exploration has always involved danger, but modern standards place greater emphasis on safety and responsibility. When robotic alternatives exist, the justification for exposing humans to extreme risk becomes less clear. This does not eliminate the desire to send people, but it does demand stronger reasons. Historically, human descents into the deepest parts of the ocean have been symbolic as much as scientific. They demonstrate what is possible. They test engineering limits. They satisfy a deep-seated urge to witness the unknown firsthand. But they are not the foundation of sustained exploration. They are exceptions, not models. Another factor is cost. Designing, building, testing, and operating a human-rated deep-sea vehicle is extraordinarily expensive. Every system must meet higher standards. Redundancy increases weight and complexity. Training crews takes time. Insurance, logistics, and support infrastructure add further expense. For the same resources, multiple robotic missions can be conducted, covering more ground and gathering more data. Human presence also alters the environment in ways that machines may not. Noise, light, and heat output are greater. Biological contamination is harder to control. In an environment as stable and slow-changing as the trench, these disturbances matter. A brief human visit may have lasting effects that are difficult to measure or reverse. Despite all this, the idea of sending humans persists. It persists because there is something fundamentally compelling about direct experience. Seeing something with your own eyes, even through a small viewport, carries a weight that data alone does not. Human observation can inspire, communicate, and contextualize in ways that instruments cannot. But inspiration alone does not overcome incompatibility. The trench is not hostile in the sense of being actively dangerous. It does not attack. It does not change suddenly. It simply exists under conditions that humans cannot tolerate without constant technological mediation. And that mediation is fragile. It must be perfect every time. This is why people don't belong there for long, not because they are unwelcome, but because they cannot relax their vigilance for even a moment. Every second at depth depends on systems functioning correctly. There is no safe baseline. There is no point at which the environment becomes manageable rather than merely survivable. As exploration continues, the role of humans becomes more indirect. We design the machines. We interpret the data. We decide where to look and what questions to ask. Our presence is felt through intention rather than occupation. This may feel unsatisfying to those who equate exploration with physical presence, but it reflects a deeper understanding of the limits involved. The trench does not need to be inhabited to be understood. It needs to be approached with respect for the constraints it imposes. Humans can visit briefly, carefully, and rarely. But long-term presence is not realistic, not with current technology, and not without unacceptable risk. From here, attention naturally turns to the machines that take our place. The fragile emissaries we send into an environment that test every assumption about durability and control. These machines extend our reach, but they too struggle, and many do not return. When humans step back from an environment because it does not tolerate them for long, machines step forward by necessity. They do not breathe, they do not panic, and they do not require comfort. In theory, they are ideal explorers for places where pressure crushes, darkness persists, and cold never relents. In practice, the machines we send into the deepest parts of the ocean are some of the most delicate tools ever built, operating in one of the most unforgiving environments on Earth. Nowhere is this tension more evident than in attempts to explore the depths of the Mariana Trench. From the outside, deep-sea vehicles look sturdy, thick hulls, reinforced frames, heavy components designed to withstand enormous forces. But this impression is misleading. Strength alone is not enough at extreme depth. Every gram matters. Every component is a compromise between durability, weight, power consumption, and function. A machine built to survive pressure may struggle to move. A machine built to maneuver efficiently may sacrifice resilience. Designing for the trench is an exercise in choosing which failures you're willing to risk. There are two main categories of machines sent into extreme depths: remotely operated vehicles connected to the surface by long tethers, and autonomous vehicles which operate independently once deployed. Each has advantages and weaknesses, and both face challenges that often end missions prematurely. Remotely operated vehicles offer the comfort of human oversight. Operators can see what the vehicle sees, make decisions in real time, and adjust behaviour based on unfolding conditions. But the tether that connects the vehicle to the surface is also a liability. At great depth, cables become heavy. Their own weight places strain on connection points. Currents can pull them sideways. Abrasion against trench walls can damage insulation. A single failure along kilometres of cable can sever communication entirely. Autonomous vehicles avoid this tether problem but introduce others. Once released, they are on their own. They must navigate, collect data, and return without guidance. Any unexpected obstacle, software error, or hardware failure can end the mission. There is no way to intervene. When autonomous probes fail, they often disappear silently, leaving behind only the last data packet they transmitted, if any. Pressure affects machines in ways that are not always intuitive. Solid-state electronics perform better than moving parts, but they are not immune. Pressure can deform circuit boards, alter connections, and cause micro-fractures that lead to intermittent failures. Insulation that works at the surface may compress and lose effectiveness. Seals that pass all tests at moderate depths may leak under extreme conditions. Even the materials chosen for deep-sea exploration behave differently under pressure. Metals may become brittle, polymers may stiffen or creep. Adhesives can fail. These changes are subtle and cumulative. A component may function perfectly on its first descent and fail on its second or third, not because conditions changed, but because stress accumulated invisibly. Power is another persistent limitation. Batteries perform poorly in cold environments. Their capacity drops. Their output becomes less predictable. Providing enough power to run cameras, sensors, propulsion, lighting, and communication systems is a constant struggle. Every watt consumed must be justified. Turning on lights improves visibility but drains energy rapidly. Turning them off conserves power but limits observation. Lighting itself presents unique problems. In total darkness, artificial light is essential, but it creates harsh contrasts. Bright beams illuminate only a narrow field, leaving everything else black. Suspended particles reflect light back toward the camera, creating snow-like interference that obscures detail. This phenomenon becomes worse the closer a vehicle gets to the seafloor, where sediment is easily disturbed. Movement near the bottom is delicate. Thrusters must be powerful enough to maneuver but gentle enough not to kick up clouds of sediment that blind sensors. Fine control is difficult under pressure, where motors respond differently and feedback is delayed. A slight miscalculation can result in collision with the seafloor or trench walls. At extreme depth, even minor impacts can damage instruments or compromise hull integrity. Navigation is another persistent challenge. GPS signals do not penetrate water, so deep-sea vehicles rely on inertial navigation systems, acoustic beacons, and dead reckoning. Errors accumulate over time. In a complex environment like the trench, with steep walls and uneven terrain, these errors can be significant. A vehicle may think it is in one location, while actually drifting dangerously close to an obstacle. Communication bandwidth is limited. Acoustic signals travel slowly and carry little data compared to radio or fiber optic communication. High-resolution video streams are difficult to transmit in real time. Often, vehicles must store data on board and transmit only summaries or status updates during the mission. If the vehicle fails before returning, that data is lost with it. This is why many machines sent into the trench do not come back. Some fail during descent, overwhelmed by pressure or cold. Others reach the bottom but suffer damage during exploration. Some lose communication and cannot be recovered. Others complete their mission but lack the power or buoyancy to ascend. Each failure teaches engineers something, but the cost is high, both financially and scientifically. Recovery itself is not guaranteed even when a vehicle surfaces. The ocean is vast. A probe may surface far from the deployment site, drifting with currents. Locating it requires coordination, luck, and time. Bad weather can delay retrieval. Rough seas can damage delicate components during hoisting. A successful dive can still end in partial loss. Despite these risks, machines remain our primary means of exploration. They are the only tools capable of operating repeatedly in an environment that tolerates neither human presence nor error. Engineers continuously refine designs, learning from past failures. Pressure housings improve, electronics are hardened, software becomes more robust. But progress is incremental. There is also an emotional dimension to these losses that is often overlooked. Research teams invest years into designing, building, and testing these machines. When one is lost, it is not just a piece of equipment that disappears, but the culmination of effort, hope, and planning. Yet loss is accepted as part of the process. The trench demands it. Interestingly, the machines themselves sometimes become part of the environment they were meant to study. Wreckage settles on the seafloor, slowly becoming just another object in the deep. Over time, it may attract life, altering the local ecosystem in subtle ways. This raises questions about long-term impact and responsibility, even as exploration continues. The fragility of these tools reinforces a central truth about the trench. It is not a place that yields easily to intrusion. Every visit is negotiated through layers of engineering compromise. Every success is partial. The data we gather is valuable precisely because it is so hard won. As technology advances, some barriers may soften. New materials, improved power systems, and smarter autonomy will extend reach and reliability. But the fundamental constraints will remain. Pressure will still press. Darkness will still absorb light. Cold will still sap energy. Machines will still fail. Understanding this helps explain why exploration of the deepest ocean progresses slowly and unevenly. It is not a matter of neglect or lack of interest. It is the result of operating at the edge of what our tools can endure. The trench does not forbid entry, but it exacts a price for every attempt. And as we consider the machines that rarely return, it becomes clear that loss is not just an unfortunate side effect. It is part of the cost of learning in a place that offers no margin for error. Each failed mission sharpens our understanding, not only of the trench itself, but of the limits of our own creations. From here, the story naturally turns toward the accumulation of these losses and what they reveal, the silent record of expeditions that ended abruptly, leaving behind fragments and unanswered questions in the darkest parts of the ocean. If you could somehow walk across the floor of the deepest ocean, if walking were possible and if pressure were kind enough to allow it, you would not find a pristine, untouched landscape. You would find traces, not many, not obvious, but present all the same. Fragments of metal, bent frames, instruments frozen in place where they stopped working. These are not ruins in the way we usually imagine them. There are no walls or roads, no signs or markers. But taken together, they form something like a quiet record of human persistence and human limitation, a scattered graveyard of attempts that went down and did not come back. The Mariana Trench has never been crowded, not by ships, not by people, and certainly not by explorers. Yet for a place visited so rarely, it has absorbed an outsized number of failures. This is not because the people who attempted these missions were careless or unprepared. Quite the opposite. It is because even the best prepared expeditions are working at the very edge of what technology allows, in an environment where mistakes do not announce themselves and recovery is often impossible. Many of these losses never make headlines. They are noted in technical reports, discussed quietly in research institutions, and remembered most vividly by the teams who built and launched the machines. A probe stops responding. A tether snaps. A signal fades and does not return. The surface crew waits, recalculates, tries again, and eventually accepts that the mission is over. The ocean does not send confirmation, does not return debris. Silence becomes the final message. One of the most unsettling aspects of these failures is how sudden they can be. At extreme depth, systems do not degrade gradually in visible ways. They hold, and then they don't. A pressure housing withstands thousands of atmospheres until one microscopic flaw propagates, and in a fraction of a second the structure collapses inward. The implosion is violent but brief. Any electronics inside are destroyed instantly. Data storage is crushed. Cameras never record their own end. From the outside, there is nothing to see. In other cases, failure is slower, but no less final. A vehicle reaches the bottom and begins its work. Hours pass. Data flows upward in thin streams. Then communication becomes erratic. Commands take longer to execute. Telemetry flickers. Eventually contact is lost altogether. The vehicle may still be intact, sitting quietly on the seafloor, but without communication or propulsion, it might as well be gone. Recovery missions are rarely attempted at such depths, and when they are, they face the same risks that caused the original failure. There are also missions that end before reaching the bottom. A descent proceeds normally for hours, pressure increasing steadily, systems reporting nominal status. Then a sensor reading shifts slightly out of range. An internal alarm triggers. Operators debate whether to abort. Sometimes they choose caution and begin ascent, only to discover that something critical has already failed. Buoyancy systems malfunction. The vehicle cannot reverse course. It continues downward until pressure finishes what malfunction began. Tethers have their own stories. Long cables stretching kilometers into the ocean are vulnerable in ways that are hard to predict. They can snag on unseen features. They can twist under their own weight. They can be damaged by abrasion or fatigue. When a tether fails, it fails completely. One moment there is a connection. The next, there is nothing. The vehicle below becomes autonomous by accident, drifting or sinking until power runs out. What makes these losses especially haunting is the lack of closure. On land, a failed expedition leaves behind wreckage that can be studied. In space, debris can sometimes be tracked. In the trench, failure often leaves no visible trace. The ocean absorbs everything. Even when the approximate location of a lost vehicle is known, locating it again is a challenge that may not be worth the risk or cost. As a result, many failures remain unresolved, their causes inferred rather than confirmed. This uncertainty complicates engineering progress. Learning from failure is essential, but when the failed system cannot be examined, lessons must be drawn indirectly. Engineers rely on pre-failure data, simulations, and assumptions. They design improvements based on what they think happened, not what they can prove happened. This slows development and increases conservatism. Every new mission carries the weight of previous losses. There is also a cumulative effect. Each lost vehicle reduces the pool of available equipment. Building replacements takes time and resources. Funding cycles move on. Teams disperse, momentum fades. A single failure rarely stops exploration entirely, but a pattern of failures can shift priorities elsewhere. The trench does not actively repel exploration, but it wears it down. The phrase graveyard is not meant to imply abundance. These losses are few compared to the number of machines humans have deployed elsewhere, but in context, they are significant. Each one represents a major investment of expertise and ambition. Each one marks a boundary that could not be crossed, at least not that time. Some of the lost machines were never intended to return. Drop probes, designed to sink, collect data briefly and transmit until they are crushed, are used deliberately in some missions. Their destruction is expected, even planned. But even these controlled losses contribute to the sense that the trench is a place where things end rather than continue. Data is extracted in the final moments before pressure overwhelms the system, like a message sent just before the line goes dead. Other losses were unintended and deeply disappointing. Vehicles that performed flawlessly in tests, that survived multiple dives at shallower depths, that reached unprecedented milestones, only to fail at the last moment. These stories circulate quietly among engineers and scientists, shaping expectations and cautioning ambition. There is also a human tendency to anthropomorphize these machines, especially when they are remotely operated. Operators spend hours watching through their cameras, maneuvering them carefully, responding to their limitations. When a vehicle is lost, it can feel less like losing a tool and more like losing a presence. This emotional dimension is rarely discussed in official reports, but it influences how teams approach future missions. The trench itself remains indifferent to all of this. It does not collect these machines intentionally. It does not alter its behavior in response to repeated intrusion. Each failure is absorbed into the background, becoming part of the slow accumulation of material on the seafloor. Over time, metal corrodes, structures collapse further, and objects blend into sediment. The environment does not remember in any meaningful way. This raises questions about how much failure is acceptable. Exploration has always involved risk, but the trench amplifies that risk while offering limited immediate reward. Each mission might yield hours of footage, samples, or measurements, but at the cost of years of preparation and the possibility of total loss. The ratio is difficult to justify outside of pure scientific curiosity, and yet exploration continues, not because failure is ignored, but because each attempt refines understanding. Even silent endings contribute indirectly. They define limits, they inform design choices, they shape expectations. The graveyard is not just a collection of losses, it is a record of where assumptions broke down. In some cases, failures reveal unexpected resilience. A vehicle believed lost surfaces days later, battered but functional. A probe transmits data long after it was expected to fail. These moments are rare but powerful, reminding researchers that the trench does not operate on a simple script. It is harsh, but not entirely predictable. The accumulation of failed expeditions also influences public perception. Stories of crushed subs and lost probes reinforce the idea that the deep ocean is uniquely hostile, perhaps more so than space. This comparison is not entirely fair, but it persists. Space failures are visible, dramatic, and often followed by recovery or redesign. Deep-sea failures vanish quietly, leaving little to analyse publicly. This quiet disappearance feeds the mystique of the trench. It becomes a place not just of depth and darkness, but of unanswered endings. Machines go down and do not return. Signals fade. The story stops mid-sentence. In a world accustomed to resolution, this is unsettling. Yet this unsettledness is part of what makes the trench compelling. It reminds us that exploration is not a guaranteed path to understanding. Some environments resist not because they are unknowable, but because knowing them requires patience, resilience, and acceptance of loss. As we move forward, the focus shifts from failure itself to what survives despite it. Not the machines, but the life forms that exist naturally in this environment, enduring pressures and conditions that crush our tools with ease. These organisms are not visitors, they are residents, and their presence raises new questions about adaptation, resilience, and what it truly means to belong in the deepest parts of the ocean. When the first instruments began returning data from the deepest parts of the ocean, many scientists assumed they would find very little life. The logic seemed straightforward. No sunlight, crushing pressure, near-freezing temperatures, and extreme scarcity of food did not sound like conditions that favoured living systems. For a long time, the deepest ocean was imagined as a biological desert, a place where survival was technically possible but barely, and where complexity would be minimal. That assumption turned out to be wrong in one of the most quietly astonishing ways science has encountered. Far below the surface, in places like the Mariana Trench, life does not merely persist. It functions. It feeds, reproduces, adapts, and maintains ecosystems that, while sparse, are stable. These organisms are not clinging to existence in a constant state of crisis. They are doing what life does everywhere else on Earth, just under conditions that seem incompatible with everything we know about biology from the surface world. One of the first surprises was not the presence of large or dramatic creatures, but the abundance of small ones. Microorganisms thrive at trench depths, forming the foundation of deep-sea ecosystems. Bacteria and archaea have been found living in sediments under pressures that would instantly kill most surface organisms. Their cellular machinery is built differently. Proteins are structured to resist compression. Cell membranes remain flexible despite cold and pressure. Enzymes continue to function where surface versions would seize up. These microorganisms do not rely on sunlight at all. Instead, they extract energy from chemical reactions involving compounds like methane, hydrogen sulfide, and ammonia. This process, known as chemosynthesis, allows life to operate independently of the sun. It is not unique to the trench, but the extreme depth pushes it to its limits. Energy availability is low, but it is steady. Over long timescales, that steadiness matters more than abundance. Larger organisms build their lives on top of this microbial foundation. Amphipods, small shrimp-like creatures, are among the most commonly observed animals at trench depths. They are not delicate or ghostly in the way deep-sea life is often portrayed. They are active scavengers, moving through sediment and water in search of food. Their bodies are compact and robust, adapted to pressure rather than speed. Their exoskeletons are flexible in ways that prevent collapse. Fish have also been observed at astonishing depths, including snailfish that live well beyond what was once thought to be the absolute limit for vertebrates. These fish lack the swim bladders used by surface fish to control buoyancy, because gas-filled spaces are liabilities under pressure. Instead, their bodies are gelatinous and dense, allowing them to hover near the seafloor without expending much energy. Their bones are less calcified, reducing the risk of fracture. Their tissues contain compounds that stabilize proteins against pressure. What is striking about these animals is not just that they exist, but that they appear well adapted rather than stressed. They are not malformed or barely functional, they are specialized. Evolution has shaped them specifically for this environment, fine-tuning their biology over millions of years. This suggests that the trench is not a marginal habitat in evolutionary terms. It is a legitimate ecological niche. Reproduction at depth follows the same pattern of patience seen elsewhere in the trench. Many deep-sea organisms reproduce slowly. Eggs are large and few in number. Development is gradual. There is little advantage to rapid reproduction when resources are scarce and conditions are stable. Instead, success favours longevity and efficiency. A single individual may live for decades, contributing slowly but reliably to the next generation. Food webs in the trench are simple but resilient. Without plants, there are fewer layers. Organic matter sinks from above, providing intermittent meals. Occasionally, a large carcass, such as a whale fall, reaches deep waters, creating a temporary surge of activity. These events are rare but significant, supporting communities that may persist for years on a single input of biomass. Between such events, life continues at a subdued pace. The existence of these ecosystems forces a reconsideration of what it means for life to thrive. Thriving does not require abundance, speed, or diversity in the way we usually define it. In the trench, thriving means persistence. It means stability. It means fitting perfectly into a set of constraints rather than overcoming them. Life does not fight the trench, it cooperates with it. From an exploration perspective, this creates both opportunity and challenge. Discovering life at such depths is scientifically invaluable. It expands our understanding of the limits of biology. It informs the search for life beyond Earth, suggesting that environments once dismissed as too hostile may be viable after all. But studying this life is extraordinarily difficult. The very adaptations that allow these organisms to survive make them fragile when removed from their environment. Bringing deep-sea organisms to the surface often kills them. Decompression damages tissues. Temperature changes disrupt metabolic processes. Even careful, gradual ascent may not be enough. As a result, much of what we know comes from in situ observation, rather than direct experimentation. Cameras capture brief glimpses. Sensors record movement and behaviour. Samples, when collected, must be preserved under pressure to remain intact. This limits the kinds of questions scientists can ask. Laboratory studies are constrained. Genetic analysis is possible, but physiological experiments are difficult. The trench offers data, but it does not offer easy access. Understanding deep-sea life becomes an exercise in inference, pattern recognition, and patience. There is also the question of how much we should interfere. Life in the trench has evolved in isolation, largely untouched by surface processes. Introducing equipment, lights, and noise alters that environment, even if only locally and temporarily. For organisms adapted to extreme stability, even small disturbances may have outsized effects. This raises ethical considerations that are still being debated within the scientific community. At the same time, the presence of life complicates the narrative of the trench as an empty or hostile void. It is not empty. It is inhabited. The inhabitants are simply not like us. They do not rely on sunlight. They do not move quickly. They do not respond to change on human timescales. They belong to an environment where patience is the primary survival strategy. This realization reframes the idea that these creatures should not exist. They should not exist according to surface-based assumptions, but those assumptions are irrelevant here. The trench operates under different rules, and life has followed those rules faithfully. The surprise is not that life exists there, but that we ever thought it wouldn't. Understanding this helps explain why exploration feels intrusive. When machines descend into the trench, they are not entering a blank space. They are entering a functioning ecosystem. The fact that it operates quietly and slowly does not make it inert. It is simply operating at a pace and scale that does not align with human expectation. This also explains why the trench does not yield dramatic discoveries on every visit. Life is present, but it does not announce itself. It does not gather in large numbers. It does not react dramatically to observers. It continues doing what it has always done, largely indifferent to being watched. As we learn more about these organisms, another question emerges naturally. How do we observe without altering? How do we study without imposing surface world assumptions on an environment that has never needed them? This question does not have a simple answer, and it leads directly into the next challenge of trench exploration, the realization that observation itself is not neutral, and that the act of looking can change the very thing being observed. In a place as stable and slow as the deepest ocean, even attention has consequences. There is a comforting idea that observation is passive, that you can look without touching, record without interfering, and study without leaving a trace. In many environments, this feels mostly true. A photograph does not alter a mountain. A telescope does not disturb a planet. But the deepest parts of the ocean do not behave this way. In the trench, observation is not neutral. Simply being there changes things, sometimes subtly, sometimes in ways that linger far longer than expected. This becomes clear very quickly in places like the Mariana Trench, where the environment has evolved around absence rather than presence. No sunlight, no storms, no frequent disturbance. Life here is adapted to consistency. When something new arrives, even something as small as a camera or a light source, it does not blend in. It stands out. The first and most obvious change comes from light. In an environment where darkness has been uninterrupted for millions of years, artificial light is not just illumination, it is an event. The moment lights switch on, they create sharp contrasts, defined shadows, and an entirely new stimulus. Organisms that have never experienced continuous brightness react in unpredictable ways. Some are drawn toward the light, others retreat. Behavior observed under illumination may not reflect natural behavior at all. This creates a fundamental problem for interpretation. If a camera records animals gathering near a light source, is that because they normally congregate there, or because the light itself is acting as an attractant? If certain species appear absent, is that because they are rare, or because they avoid the disturbance? There is no easy way to separate observation from influence. Sound is another disruptive factor. Deep-sea vehicles generate noise even when designed to be quiet. Motors hum, thrusters push water, structural components vibrate. In the deep ocean, sound travels far and persists longer than in air. A vehicle descending into the trench announces its presence acoustically long before it arrives visually. Organisms that rely on subtle vibrations to detect food or danger may alter their behavior in response. Even movement itself is disruptive. The seafloor of the trench is covered in fine sediment that has settled slowly over long periods. When a vehicle approaches too closely or maneuvers abruptly, it stirs up clouds of particles that can remain suspended for extended periods. These clouds reduce visibility and may alter local conditions, affecting feeding and movement patterns of nearby organisms. Chemical changes also occur. Every vehicle introduces foreign materials into the environment. Metals, plastics, lubricants, and coatings interact with seawater. Even when designed to be inert, they represent a deviation from the trench's baseline chemistry. Heat generated by electronics creates microenvironments warmer than the surrounding water. These changes are localized, but in an environment where change is rare, even small deviations matter. There is also biological contamination to consider. Microorganisms from the surface can be carried down on equipment despite sterilization efforts. Most will not survive, but some may persist temporarily. Introducing new biological material into an isolated ecosystem raises concerns about unintended consequences, even if those consequences are difficult to measure. The act of sampling intensifies these effects. Collecting sediment or organisms removes material that took centuries or millennia to accumulate. A single sample may seem insignificant, but repeated sampling in the same area can alter the local environment. Tracks left by vehicles may persist for decades, not because the environment is fragile, but because there are no processes to erase them quickly. This persistence challenges the assumption that deep-sea environments are resilient simply because they are vast. The trench is large, but activity tends to concentrate around accessible or scientifically interesting sites. These sites may receive repeated visits, amplifying impact. Over time, the cumulative effect of observation can become significant. There is a psychological component as well. Knowing that observation alters the environment creates hesitation. Scientists must balance curiosity with responsibility. Each decision to deploy a vehicle, turn on a light, or collect a sample carries weight. This slows exploration, not because of indecision, but because caution becomes part of the methodology. The phrase, "the trench that watches back," captures this dynamic. It is not watching in a conscious sense, but it responds. It records disturbance in ways that last. It reflects our presence back at us through altered behaviour, disturbed sediment, and lingering traces. Unlike surface environments that absorb and mask human activity quickly, the trench preserves it. This awareness has led to changes in how exploration is conducted. Lighting is minimised. Vehicles are kept at greater distances from the seafloor. Non-invasive observation techniques are prioritised. Long-term monitoring devices are favoured over repeated short visits. Even so, complete non-interference is impossible. To observe is to alter. This reality reshapes expectations. Exploration is no longer about exhaustive documentation. It becomes selective. Researchers must choose what is worth disturbing and what is better left alone. Questions are refined, objectives narrowed. The trench does not offer unlimited access, and observation is treated as a privilege rather than a right. Understanding that observation changes the environment also complicates public perception. Footage from the deep ocean often appears serene and untouched, giving the impression that exploration is harmless. The reality is more nuanced. Each image represents a moment of disruption, however brief. Each mission leaves a trace, however small. This does not mean exploration should stop. It means it must proceed thoughtfully. The goal shifts from conquering or cataloguing to understanding without overwhelming. The trench does not resist exploration through hostility, but through sensitivity to disturbance. As technology improves, new methods may reduce impact further. Better sensors, lower light cameras, quieter propulsion systems. But the fundamental issue remains: presence changes things. In an environment defined by stability, change is amplified. Recognizing this helps explain why trench exploration advances cautiously. It is not just the difficulty of getting there or surviving once arrived. It is the knowledge that every visit matters, that the act of looking carries consequences. And this leads naturally to another limitation, one less visible, but just as restrictive. Even when we observe carefully, even when machines survive and data is collected, communication itself becomes a bottleneck. Down here, information does not move freely. Sound behaves strangely. Signals arrive late or distorted. And understanding the trench becomes as much about how we communicate with it as how we look at it. When light disappears, sound takes over. Not as a replacement in any comforting sense, but as the only practical way to reach across distance in the deep ocean. In the abyss, sound becomes the primary messenger, the thin thread connecting machines at depth to the humans waiting far above. And yet sound does not behave politely down here. It bends, stretches, scatters, and sometimes vanishes altogether, turning communication into one of the most persistent and underestimated challenges of trench exploration. In places like the Mariana Trench, sound is not just a tool, it is a constraint. Every instruction sent downward, every fragment of data sent upward, must travel through kilometres of cold, dense water that shapes and distorts it along the way. Unlike radio waves, which fade quickly underwater, sound can travel long distances. This makes it indispensable. But distance alone does not guarantee clarity. Water is not a uniform medium. Temperature, salinity, and pressure all influence how sound moves. Near the surface, sound waves scatter unpredictably due to waves, bubbles, and temperature gradients. As depth increases, conditions become more stable, but pressure rises and temperature drops, changing the speed at which sound travels. Instead of moving in straight lines, sound waves bend, refract, and curve, following paths that are difficult to predict precisely. This creates zones where sound travels farther and zones where it fades unexpectedly. A signal sent downward may arrive weaker than expected or arrive at a slightly different angle. Echoes bounce off trench walls, overlap and return delayed. Distinguishing between a direct signal and a reflection becomes a technical puzzle. Communication systems must filter noise, correct timing errors, and interpret incomplete information. Latency is unavoidable. Sound travels through water at roughly 1/500 meters per second, which sounds fast until you consider the distances involved. A signal sent to the bottom of the trench may take several seconds to arrive. A response takes just as long to return. This delay eliminates the possibility of real-time control. Operators cannot steer a vehicle instant by instant. They must anticipate, command, and wait. This fundamentally changes how exploration unfolds. Commands are issued cautiously, often in batches. Operators send instructions, then pause to see how the vehicle responds. If something goes wrong, correcting it takes time. In emergencies, those seconds matter. A delayed response can mean the difference between recovery and loss. Bandwidth is another severe limitation. Sound cannot carry large amounts of data efficiently. High-resolution video streams, which are routine in shallow water exploration, become impractical at extreme depth. Instead, vehicles compress data aggressively or store it on board for later retrieval. What reaches the surface in real time is often a simplified version of reality, reduced to essential telemetry and low-bandwidth imagery. This reduction shapes perception. Operators see a narrow slice of what the vehicle encounters. Details are missed. Context is lost. Decisions are made based on partial information. This is not due to negligence, but necessity. The communication channel simply cannot support more. Noise complicates matters further. The ocean is not silent, even at great depth. Distant ship traffic, seismic activity, and biological sounds all contribute to a background hum. Some animals produce low-frequency sounds that travel astonishing distances. These noises can interfere with communication signals, creating interference that must be filtered out. Differentiating between meaningful data and ambient noise becomes a constant task. Equipment itself adds to the noise. Thrusters, motors, and structural vibrations generate sound. Even careful design cannot eliminate it entirely. In a medium where sound travels so efficiently, these self-generated noises can mask incoming signals or distort outgoing ones. Engineers must design systems that are not only functional but acoustically considerate. Navigation relies heavily on sound as well. Without GPS, deep-sea vehicles use acoustic beacons placed on the seafloor or deployed from the surface. By measuring the time it takes for sound pulses to travel between beacons and the vehicle, operators can estimate position. This method works, but it is imprecise. Errors accumulate. Reflections from trench walls introduce uncertainty. Over time, a vehicle's estimated position may drift significantly from reality. This uncertainty affects mission planning. Vehicles must keep safe distances from terrain they cannot see clearly. Exploration proceeds slowly, with frequent pauses to recalibrate position. Ambitious maneuvers are avoided. The environment dictates caution, not curiosity. Communication failures are among the most common causes of lost vehicles. A damaged transducer, a software glitch, or unexpected interference can sever the acoustic link. When communication stops, operators are left with a difficult choice. Wait and hope the connection re-establishes, or assume the worst and terminate the mission. Sometimes communication resumes hours later. Sometimes it never does. Even when communication functions as intended, it imposes a psychological distance. Operators are separated from the environment not just physically but temporally. They react to what has already happened, not what is happening now. This lag creates a sense of detachment, as if exploration is always slightly out of sync with reality. For autonomous vehicles, the communication problem is even more stark. These machines must operate largely without contact, making decisions based on pre-programmed logic and sensor input. They may surface periodically to transmit data, but during descent and exploration they are effectively isolated. Any unforeseen situation must be handled internally. If the software encounters a scenario it cannot resolve, failure follows. This reliance on autonomy raises difficult questions. How much decision-making should be delegated to machines in an environment where communication is limited? How do you anticipate every possible condition? The trench is complex, and our understanding of it is incomplete. Designing software that can handle unknowns is an ongoing challenge. The strange behaviour of sound also affects scientific measurements. Acoustic instruments are used to map the seafloor, detect movement, and study biological activity. Interpreting this data requires careful calibration. Echoes may represent terrain, organisms, or artifacts. Distinguishing between them requires experience and often corroboration from other sensors. In some cases, sound reveals things that vision cannot. Movements beyond the range of lights can be detected acoustically. Distant events leave signatures in the water, but these insights come with ambiguity. Sound paints a picture in broad strokes, not fine detail. It suggests rather than shows. This ambiguity feeds into the trench's resistance to exploration. Knowledge arrives indirectly, filtered through layers of interpretation. Certainty is rare. Conclusions are provisional. Every dataset carries caveats. This slows progress, but it also enforces humility. The environment does not offer clear answers quickly. Communication limitations also affect collaboration. Data arrives slowly and in fragments. Analysis takes time. Sharing results across institutions is delayed. The pace of discovery is measured in years rather than weeks. In a world accustomed to rapid information exchange, this can feel frustrating. Yet this slowness is not accidental. It is imposed by the environment. The trench does not accommodate high-speed interaction. It insists on patience. Sound may travel farther than light down here, but it still travels on the trench's terms. Understanding this helps explain why exploration feels tentative. It is not just about surviving pressure or navigating darkness. It is about working within a communication system that resists immediacy. The abyss does not respond instantly. It responds slowly, imperfectly, and sometimes not at all. As exploration continues, engineers and scientists refine acoustic techniques, developing better signal processing, smarter compression, and more resilient systems. Progress is steady, but limits remain. Sound will always be slower than light. Water will always distort signals. Distance will always impose delay. And so, communication in the abyss remains a careful conversation, one where listening is as important as speaking, and where silence often carries as much meaning as sound. This realization leads naturally to another subtle effect of the trench environment, one that shapes not just communication, but perception itself. Down here, time does not seem to move the way it does at the surface, and exploration begins to slow, not just technologically, but psychologically. At the surface, time feels busy. Hours are divided, minutes accounted for, schedules stacked tightly together. Movement is fast, communication is immediate, and progress is measured in visible steps. But as exploration descends into the deepest parts of the ocean, something subtle happens to time itself. Not in the relativistic sense measured by physics, but in the lived sense experienced by those who plan, conduct, and interpret deep-sea exploration. At the bottom, especially in places like the Mariana Trench, time stretches, slows, and resists being compressed into human expectations. This slowing begins long before anything reaches the seafloor. Planning a single deep-sea mission can take years. Designs are reviewed repeatedly. Components are tested and retested. Simulations are run under countless scenarios. Every decision is weighed against the cost of failure, because failure at depth is rarely quick to recover from, if it can be recovered from at all. Where surface exploration can afford iteration, deep exploration must aim for correctness on the first attempt. Once a mission finally begins, time continues to behave differently. Deployment itself is slow. Ships must reach precise locations, often far from land. Weather windows matter, not because the trench is affected by storms, but because surface operations are. Lowering equipment into the water takes hours. Descent takes hours more. During this time, there is little to do but wait and monitor instruments as pressure increases steadily. There is no way to speed this up without increasing risk. At depth, operations slow further. Movement near the seafloor is cautious and deliberate. Vehicles advance meter by meter, sometimes centimeters at a time. Each maneuver is planned, executed, observed and evaluated before the next begins. Thrusters are used sparingly, lights are adjusted carefully, sensors are activated selectively. Nothing happens quickly because nothing can afford to happen quickly. Communication delays reinforce this pace. Commands take seconds to arrive, responses take seconds to return. In aggregate, these delays stretch interactions into long, drawn-out exchanges. An adjustment that would take moments on land may take minutes or longer at depth. If something unexpected occurs, diagnosing it can take hours as partial information trickles back to the surface. Even successful missions spend surprisingly little time actually observing. A descent that takes half a day may yield only a few hours at maximum depth. Those hours are precious and tightly scheduled. Cameras must capture specific targets. Samples must be collected efficiently. There is no time to wander or improvise. Exploration becomes less about discovery in the moment and more about executing a predefined plan. After ascent, time stretches again. Data must be downloaded, verified, and backed up. Video footage is reviewed frame by frame. Sensor readings are calibrated and corrected. Anomalies are debated. Interpretations are cautious. A single dive may generate months or years of analysis. Discoveries emerge slowly, not because they are unimportant, but because confidence takes time. This slow pace contrasts sharply with public expectations. In an era of rapid information, there is an assumption that exploration produces immediate results. Images are expected quickly. Answers are expected promptly. The trench does not comply. It yields information at a rate dictated by physics, engineering, and caution, not by attention cycles or funding timelines. Time also moves differently psychologically. For those involved in deep-sea exploration, patience becomes a skill. Waiting is not idle. It is active, attentive, and necessary. Teams learn to value incremental progress. A single successful data point can justify months of effort. Small improvements matter. A slightly clearer image, a more stable sensor reading, a few extra minutes of operation time can represent meaningful advancement. At the bottom, there is also a sense that the environment itself is indifferent to urgency. The trench does not change in response to human schedules. It does not become more accessible if approached quickly. It does not reward haste. In fact, haste is punished. Mistakes made in a rush are often final. This enforces a cultural shift among explorers, away from speed and toward deliberation. The organisms that live there reinforce this perspective. Their lives unfold slowly. Growth takes years. Reproduction is infrequent. Change is subtle. Observing them requires matching their pace rather than imposing ours. Long-term monitoring becomes more valuable than short-term observation. Patterns emerge only over extended periods. This slow rhythm affects funding and institutional support as well. Projects that take decades to mature struggle to compete with initiatives promising faster returns. The trench demands long-term commitment, but human systems are often short-term. This mismatch further slows exploration, not because of lack of interest, but because of structural constraints. Time also stretches in the face of uncertainty. When a mission fails or data is inconclusive, resolution may take years, if it comes at all. Questions linger, hypotheses remain provisional. The trench does not offer quick validation. Knowledge accumulates gradually, layer by layer, much like sediment settling on the seafloor. There is also the weight of waiting between missions. Ships are booked. Equipment is repaired or rebuilt. Teams disperse and reassemble. Momentum ebbs and flows. Exploration does not proceed continuously, but in pulses separated by long intervals. Each return to the trench feels like picking up a conversation after years of silence. From the outside, this can look like stagnation. In reality, it is a different mode of progress, one that values durability over speed, depth over breadth, and certainty over spectacle. Time at the bottom enforces this mode relentlessly. Even the language used by researchers reflects this shift. Words like incremental, preliminary, and long-term appear frequently. Conclusions are careful, claims are modest. This is not caution born of fear, but of experience. The trench has taught that rushing leads to loss, and loss leads to more waiting. Understanding that exploration slows to a crawl at depth helps explain why the trench remains largely unexplored. It is not because effort is lacking, it is because the environment imposes a tempo that does not align with human impatience. Progress happens, but on a timescale that feels almost geological. As attention turns forward, this altered sense of time raises another question. If exploration is slow, difficult, and costly, what tools can realistically extend our reach? How do we see what lies below when even direct observation is constrained by depth and delay? This question points upward, not downward, toward the limits of observation from above, and why even our most advanced vantage points cannot simply look down and solve the mystery. From the outside, it seems like a simple question. We have satellites orbiting Earth that can read license plates, track weather systems in real time, and map distant planets with astonishing precision. They watch forests grow and shrink, ice sheets crack, cities expand, and oceans warm. So why can't they just look down and show us the deepest parts of the ocean? Why does a place like the Mariana Trench still resist being seen from above? The answer lies in a quiet mismatch between how satellites work and how the ocean behaves. Satellites are masters of surfaces. They excel at detecting reflected light, emitted radiation, and subtle changes in elevation. What they cannot do is see through kilometers of water. Water absorbs and scatters electromagnetic radiation extremely efficiently. Light penetrates only a short distance before it is lost. Infrared, ultraviolet, and visible wavelengths all fade quickly. Radar can skim the surface, but it cannot pass through. From space, the ocean is opaque. This means that satellites do not observe the seafloor directly. They never have. Every image of the deep ocean floor is the result of indirect methods, inference layered on top of measurement. Satellites can tell us a great deal about the ocean's surface, but the moment you ask what lies beneath, their vision ends. What satellites can do instead is measure gravity. Massive features on Earth, including mountain ranges and deep trenches, slightly alter the planet's gravitational field. These variations are tiny, but satellites equipped with sensitive instruments can detect them. Over a trench, the pull of gravity is slightly different than over a flat plane. This difference affects the height of the ocean surface by a small amount, sometimes just a few centimeters spread over many kilometers. By measuring these subtle bulges and dips in the sea surface, scientists can infer the general shape of the seafloor below. This technique, known as satellite altimetry, has revolutionized our understanding of large-scale ocean features. It allows us to identify underwater mountain chains, plate boundaries, and broad trench systems. Without it, vast portions of the ocean floor would still be entirely unknown. But this method has limits that become painfully obvious in places like the Mariana Trench. Gravity-based mapping is inherently low resolution. It smooths out detail, sharp edges are blurred, narrow features are averaged away. A deep, thin trench becomes a broad depression in the data. Fine structure disappears. The deepest point might be inferred, but its exact shape, slope, and surrounding features remain uncertain. This is not a flaw in the technology. It is a consequence of physics. gravity signals weaken with distance. By the time a satellite detects a gravitational anomaly caused by the seafloor, that signal has travelled through kilometres of water and atmosphere. Only the largest, most massive features leave a clear imprint. Smaller variations are lost in noise. Even more advanced satellites cannot overcome this limitation. Higher sensitivity improves detection slightly, but it does not change the fundamental problem. You cannot resolve fine details of something buried under kilometres of dense material by measuring its gravitational influence from space. The information simply is not there to extract. There is also a misconception that satellites can use sonar-like techniques from orbit. They cannot. Sound does not travel through space. Even if it did, it would not penetrate water in a useful way. Sonar requires proximity. It requires transmitting sound waves into the water and receiving echoes. That can only be done from ships, buoys, or submerged vehicles. This leads to a stark contrast. We can map the surface of Mars in exquisite detail, but we struggle to map our own planet's deepest regions. Mars presents an exposed surface with little atmosphere and no oceans to obscure it. The Mariana Trench is hidden beneath the most effective natural shield imaginable. Water blocks sight, absorbs energy, and isolates what lies below. Satellites also cannot solve the problem of scale. Even if indirect methods reveal the general outline of the trench, they cannot capture the small-scale features that matter most for understanding it. The steep walls, the uneven floor, the microhabitats where life concentrates, the scars left by tectonic movement. These details require close observation. They require instruments to be physically present. There is a temptation to believe that future technology will simply bypass these limits, that a new generation of satellites will somehow see through water or reconstruct the seafloor perfectly from orbit. But this belief underestimates the stubbornness of physical constraints. Technology advances, but it does not rewrite fundamental properties of matter. Water will still absorb light, gravity will still blur detail, distance will still dilute signals. This does not mean satellites are useless for deep-sea science. On the contrary, they are essential. They provide context, they guide exploration, they help identify where to look and where not to waste effort. Without satellite data, trench exploration would be blind and inefficient. But satellites are scouts, not witnesses. They point the way without revealing the destination. The reliance on satellites also shapes expectations. Because satellite imagery elsewhere feels immediate and authoritative, there is an assumption that unseen places are simply unexamined rather than unobservable. The trench challenges this assumption. It is not unseen because no one bothered to look. It is unseen because looking from afar does not work. This gap between expectation and reality feeds frustration. Why is progress slow? Why are maps incomplete? Why does uncertainty persist? The answer is that modern technology is powerful but not universal. It excels under certain conditions and fails under others. The deep ocean happens to sit squarely in one of those failure zones. Understanding this reframes the trench's resistance to exploration. It is not defying our tools out of mystery or drama. It is simply beyond the reach of certain methods. To understand it, we must accept slower, riskier, more localized approaches. Ships, probes, and patience replace satellites and instant clarity. This acceptance is difficult in a world accustomed to rapid answers. It feels inefficient, it feels backward, but it reflects a deeper truth about exploration. Some places cannot be observed from a distance. They demand proximity, they demand effort, and they demand acceptance of limits. As we continue, this realization naturally leads to a more uncomfortable question. If our tools cannot easily reveal the trench, and if every descent carries risk and disturbance, what motivates us to keep trying? What do we expect to find that justifies the effort? And beneath that, what are we quietly afraid might be waiting in a place that has remained hidden for so long? There is a certain comfort in ignorance when the unknown is safely distant. When something lies beyond reach, it can remain abstract, stripped of consequence. But the deepest parts of the ocean are not distant in the cosmic sense. They are here, on this planet, beneath routes we travel and weather systems we track. They are close enough to matter, yet far enough to resist understanding. And in that space between proximity and obscurity, a quieter question begins to form, one that is rarely stated directly. What are we afraid to find down there? This question is not about monsters or myths, though those ideas often surface in popular imagination. It is about uncertainty, about the possibility that what lies beneath the pressure may complicate what we think we know about Earth, about life, and about our place within both. The Mariana Trench is not frightening because it is dramatic. It is unsettling because it is indifferent, because it exists beyond our systems of meaning and control. One source of unease comes from scale. The trench is not just deep. It is deep in a way that distorts perspective. We are accustomed to thinking vertically in manageable terms. Buildings rise a few hundred meters, mountains climb a few kilometers, aircraft cruise above the clouds. The trench extends downward beyond all of that, into a region where the surface world becomes irrelevant. This scale alone challenges intuition. It forces us to confront the fact that much of our planet operates outside the range of direct human experience. Within that scale lies the possibility of surprise. Every time instruments have reached extreme depths, they have found something unexpected, not always something dramatic, but something that did not fit neatly into prior models. New species, unexpected chemical processes, anomalies in sediment composition. Each discovery has been small, but collectively they suggest that our understanding of deep ocean systems is incomplete. This incompleteness is unsettling because it implies vulnerability. Earth's systems are interconnected in ways we are still uncovering. The deep ocean plays a role in carbon storage, nutrient cycling, and long-term climate regulation. If processes in the trench behave differently than assumed, those differences could matter on a planetary scale. The fear is not of immediate catastrophe, but of hidden complexity, of feedback loops we have not accounted for. There is also the question of life's limits. Discoveries of organisms thriving under extreme pressure and scarcity have already forced revisions of biological theory. Each new finding pushes the boundary of what is considered possible. This is exciting, but it also raises questions. If life can exist here, under conditions once thought prohibitive, where else might it exist? And what does that say about our definitions of habitability, of normalcy, of resilience? These questions extend beyond Earth. The deep ocean is often compared to environments on icy moons or distant planets. Studying life in the trench informs the search for life elsewhere, but it also removes some comforting constraints. If life does not require sunlight, moderate pressure, or abundant energy, then it may be far more widespread and far more alien than we imagine. The fear here is not of life itself, but of how much we may not recognize it when we see it. Another layer of discomfort comes from contamination. Humans have a long history of altering environments, often unintentionally. The trench has remained relatively isolated, but not entirely untouched. Microplastics have been found at depth. Chemical pollutants sink slowly and accumulate over time. Each descent introduces foreign materials, however carefully controlled. There is an unspoken concern that by exploring, we may be damaging something we barely understand. This concern is amplified by the trench's slow pace of change. In an environment where recovery takes centuries or longer, mistakes persist. A disturbance that would be temporary elsewhere becomes effectively permanent here. The fear is not just of what we might find, but of what we might do, and of not knowing the consequences until it is too late to reverse them. There is also fear rooted in data itself. Scientific exploration often reveals complexity that resists simple explanation. Models become less certain. Predictions acquire larger error bars. Confidence gives way to probability. The trench, by offering limited fragmentary data, exacerbates this effect. Each new dataset answers some questions and raises others. The picture never quite resolves. For institutions and policymakers, uncertainty is uncomfortable. Decisions require clarity. Funding requires justification. The trench does not offer clear narratives of progress or utility. Its value is long-term, diffuse, and difficult to quantify. This makes it harder to integrate into decision-making frameworks that favour immediate outcomes. The fear here is bureaucratic rather than existential, but it still shapes what gets explored and what does not. There is also a more personal dimension to this fear, one tied to control. Humans are accustomed to shaping environments to suit their needs. Even in extreme places, we build shelters, regulate temperature, impose structure. The trench resists this impulse. It cannot be tamed or domesticated. Our presence there is always provisional, dependent on technology that can fail without warning. This lack of control is deeply uncomfortable. In many ways, the trench reflects back our own limitations. It shows us an Earth that does not revolve around human activity, that operates on timescales and under conditions we cannot easily influence. It reminds us that mastery is partial, that knowledge has boundaries. This is not a message humans are particularly fond of receiving. The fear of the unknown also intersects with storytelling. We are drawn to narratives with beginnings, climaxes, and resolutions. The trench does not provide these. It offers fragments, short visits, incomplete records, silent failures. The story never feels finished. For some, this is frustrating. For others, it is unsettling. We prefer mysteries that can be solved, not ones that persist indefinitely. There is also the lingering awareness that the trench is not static forever. Geological processes continue, tectonic plates shift, sediments accumulate, chemical gradients evolve. Over millions of years, the trench will change, perhaps disappear. Studying it now captures a fleeting moment in planetary history. The fear is that we may miss something important by not looking closely enough while we still can. And yet, there is hesitation. Not because of a single danger, but because of accumulation, pressure, darkness, cost, risk, disturbance, uncertainty. Each factor alone is manageable. Together they create a weight that slows action. The unknown beneath the pressure is not a single revelation waiting to be uncovered. It is a complex, layered reality that resists simplification. This resistance shapes our relationship with the trench. We approach cautiously. We choose limited objectives. We accept partial answers. We leave much unexplored. Not because we lack curiosity, but because curiosity alone is not sufficient. Exploration requires justification, and the trench challenges us to articulate why knowing matters. Perhaps what we are most afraid to find is not something alien or dangerous, but something familiar in an uncomfortable way. A reminder that Earth is still largely beyond our grasp, that there are systems operating quietly beneath our feet and beneath our oceans that we do not fully understand, that our maps, models, and narratives are provisional. In this sense, the fear is not of discovery, but of humility. The trench asks us to accept that some parts of our world will remain partially unknown, not because they are inaccessible forever, but because understanding them requires patience, restraint, and a willingness to live with uncertainty. As exploration continues, this fear does not disappear. It evolves. It becomes part of the process, a check on ambition, a reminder to proceed thoughtfully. The unknown beneath the pressure remains, not as a threat, but as an invitation to reconsider how we define exploration itself. And as we begin to consider the future of trench exploration, another question naturally arises. If the deepest parts of the ocean resist us so effectively, if they change slowly and respond poorly to disturbance, perhaps the most responsible choice is not to push harder, but to step back. To consider whether leaving some places largely untouched is not a failure of curiosity, but an expression of it. There is a moment in every long effort of exploration when the question quietly changes. It stops being about how to reach a place and starts being about whether reaching it is the right thing to do at all. With the deepest parts of the ocean, and especially with the Mariana Trench, that moment has arrived more than once. Each time it has nudged exploration not forward, but sideways, into reflection. The trench remains mostly untouched, not because it has been forgotten, and not because humans lack the ability to reach it. It remains untouched because every attempt to engage with it reveals how little benefit comes from intrusion and how much value lies in restraint. This is an uncomfortable conclusion in a world that often equates progress with presence and understanding with access. Leaving the deep undisturbed is not the same as ignoring it. The trench is studied, discussed, modelled, and monitored. Data is collected indirectly. Samples arrive rarely and carefully. Observations are made with increasing awareness of their consequences. What has changed is not curiosity but attitude. Exploration here has become less about conquest and more about coexistence at a distance. One reason for this shift is scale. The trench is not a single site that can be thoroughly examined and then checked off a list. It is vast, complex and layered. Fully exploring it would require a level of sustained presence that current technology cannot support without unacceptable risk and disruption. Each mission touches only a tiny fraction of the whole. The idea of comprehensiveness becomes unrealistic. Another reason lies in fragility that is not obvious at first glance. The trench does not look delicate. It does not crumble or erode rapidly. It does not depend on constant renewal. But its stability is precisely what makes it sensitive. Changes linger. Disturbances persist, introducing noise, light, heat, or foreign material into an environment that has evolved without them for millions of years carries consequences that unfold slowly and quietly. There is also the issue of diminishing returns. Early exploration yielded dramatic revisions to scientific understanding. Life existed where it was not expected. Chemistry behaved differently. Pressure reshaped biology. As knowledge accumulates, new discoveries become more subtle. They matter, but they do not justify the same level of disruption. The balance between insight gained and impact caused becomes harder to defend. Economic realities reinforce this balance. Deep sea exploration is expensive. Ships, crews, vehicles, and years of preparation are required for brief windows of observation. When weighed against other scientific priorities, the trench often loses not because it is unimportant, but because it is inefficient in a narrow sense. Its value lies in depth of understanding, not breadth of application. Ethical considerations also play a role. There is growing recognition that not every environment needs to be fully accessed to be respected or valued. The trench represents one of the few places on Earth that remains largely free from continuous human presence. Preserving that condition has meaning, both scientifically and culturally. It serves as a reminder that restraint is a form of stewardship. This does not mean exploration has stopped or will stop. It means it has slowed and become more selective. Long-term monitoring instruments replace repeated visits. Passive observation is favoured over active manipulation. Questions are chosen carefully, and some are deliberately left unanswered. The trench teaches patience by demanding it. There is also a quiet humility in acknowledging limits. Humans are adept at extending their reach, but not every extension leads to wisdom. The trench exposes the gap between what can be done and what should be done. Accepting that gap is not a failure of ambition. It is a recognition of context. Leaving the deep undisturbed also reshapes how we think about knowledge itself. Understanding does not always require direct contact. Models, indirect measurements, and long-term observation can reveal patterns without intrusion. The trench challenges the assumption that seeing everything up close is the only valid form of knowing. Perhaps most importantly, the trench remains untouched because it does not ask to be explored. It does not offer resources that demand extraction. It does not threaten the surface world in ways that require immediate intervention. It simply exists, quietly and persistently, under conditions that resist haste. In that sense, leaving it undisturbed is not abandonment, it is acknowledgement. An acknowledgement that some parts of the planet operate on timescales and under conditions that do not align with human urgency. That not all mysteries need to be solved immediately. That presence is not always improvement. The trench will remain where it is long after current technologies are obsolete. It will continue to accumulate sediment, host life adapted to pressure, and shape the planet's geology whether we watch or not. Choosing to step back does not diminish its importance, it highlights it. And so the deepest place on Earth remains mostly untouched, not because it has defeated us, but because it has taught us something quietly valuable. That exploration is not only about going further or deeper, but about knowing when distance itself is the most respectful position to take.